I want to look at a corollary to the inverse function theorem, something we easily get immediately after proving the inverse function theorem, which is that if f is a C1 function, a continuously differentiable function, from an open set E of a subset of Rn to Rn, with also the derivative of f being differentiable, with the derivative f being invertible everywhere, and f prime x invertible for all x in E, then f is an open map. It's an open map. And open, I think we have not really talked about this concept in this course. So open means the image of any open set is open. So for all G subset E, for all open G subset of the domain, f of G is open. The image of G is open. So of course, if f is continuously differentiable, so it's differentiable, then it is a continuous map. It's at least a continuous map. So the preimage of any open set is open. This does not imply that the image of any open set is open. So having the image of any open set be open is definitely something else. Let me give you an example of a non-open map, just to motivate this. So take a function from R to R given by f of x equals x squared. So this is definitely a continuous function, right? But so the preimage of any open set is open. However, let me try to draw a graph. However, if you take the image of an open set, that definitely need not be open. So for example, let me take the image of the open interval from -1 to 1. So let me take the image of this open interval. What do I get? I get this closed interval from 0 to 1, right? So the image of this open set is definitely not open. Definitely not open, because 0 is not in the interior of this. There's no neighborhood of 0 that lives inside this. Or this is not a neighborhood of 0. Okay, so being an open map is kind of something special. So that's pretty awesome that we can get that conclusion by checking something having to do with the derivative. Notice that this assumption about f prime x being invertible is stronger than just what appears in the inverse function theorem. We're not just saying f prime is invertible at one place. We're saying it's invertible everywhere. If f prime x is everywhere an invertible linear map, then you get f as an open map. Another bit of significance to the idea of open map is if you have a okay, so this will make sense if you've had some topology. There's a difference between a continuous bijection and a homeomorphism. A homeomorphism is a true equivalence of topological spaces. It would be a continuous function which is invertible and whose inverse is continuous. So more than just a continuous bijection. A continuous bijection with continuous inverse. Now we have seen, I think we saw in 118b, that one way to describe continuity is to say, well, a function is continuous if and only if the preimage of any open set is open. So if you have a continuous bijection, then the preimage of any open set is open. What's left to have it be a homeomorphism, a topological equivalence? What's left is for it to be an open map. For its inverse, for the inverse of a function to be continuous, the function has to be an open map. Because for the inverse of a function to be continuous, the preimage of any open set under the inverse has to be open. So the function has to be an open map. So this is providing us with, in some situations, a way to prove that some functions are homeomorphisms by checking their derivative. Okay, so this is a corollary, so that means it's way easier to prove than the inverse function theorem, but that doesn't mean it's immediate. So we'll prove it in the next video.